We discuss today the operation in quantum field theory, in particular in the operation which acts on the Dirac equation, and this operation of charge conjugation, which actually allows us to understand the notion of antiparticles. And to do this, we have first to understand how Dirac particle interacts with an electromagnetic field. And this we need in order to, first of all, be able to introduce the notion of electric charge in the context of a Dirac particle. Because so far, our Dirac equation did not involve electric charge at all. On the other hand, we understand that the properties of the electron concerning its electric charge only show up when we put our electron in an external electromagnetic field. So there should be electromagnetic field around, which then influences the motion of our electrically charged particle. And so then we see indeed that there is a coupling of this particle to surrounding electromagnetic field, and tracing the change of the particle trajectory, we therefore will be able to detect the presence of electromagnetic field around on the one hand side, and on the other hand side to say that our particle possesses a property which we call electric charge. In other words, the ability of our particle to interact with electromagnetic field. Therefore, the first step would be to introduce the coupling of the Dirac spinor, of the Dirac particle, to an external electromagnetic field. So in this case, I consider, therefore, electromagnetic field as being external, has been given to us. And as we know from classical electrodynamics already, the electromagnetic field is defined by means of a potential, electromagnetic potential, A mu. And I will just write down how we introduce this electromagnetic field in the Dirac equation. This is done in the following way. So gamma mu I h bar d mu minus E divided by C A mu minus MC acting on a spinor psi gives 0. So here I write this equation with all the constants, with all the physical constants. So you see h bar, speed of light, and E here is a charge of our Dirac particle. So E was something which we call charge, no, electric charge of a Dirac particle. No, mass as usual is a mass. So in other words, the introduction of the potential amounts to a procedure of, as people sometimes say, making the usual derivative to become longer, to become long derivative. Long derivative means that we extend d over d mu by adding to it the electromagnetic potential A mu. And in fact, this quantity I h bar d over dx mu minus E divided by C A mu in differential geometry would get a name of covariant derivative. Covariant derivative where A mu is considered to be a connection on a certain bundle. Let me not go for the moment into this mathematical description, this mathematical trickery. For us, a mu will be just electromagnetic potential given in the whole space-time, so it's a function of a space-time point x, and this is an equation we have now to consider. Now, in natural units, electric charge has a physical dimension of square root of h bar c. So I think I already mentioned this a couple of times. Let me write it again. I will write it schematically in the form that dimension of this quantity E is the same as dimension of square root of h bar c. And this is useful to have in mind that electric charge has such a dimension, that's the same dimension as square root of h bar c in terms of fundamental constants. And this fact can be deduced already from the Coulomb force between two equal charges, because as we know, the Coulomb force between two such charges simply E squared divided by R squared by the distance between these charges. So charges are equal, and this is the force then. And from here you see that E squared, the dimension of E squared, is the same as the dimension of force multiplied by length squared. And this I can write as a force multiplied by length, and then another length I will represent as t time multiplied by speed of light, tc, so this is another length, and then f multiplied by length, so force by length is work, or work is the same as energy, and energy multiplied by time is Planck constant, h bar, and then c, and then you see that this is dimension h bar c, and then taking square root, you get the dimension of electric charge. Okay, so this is a simple fact which is useful to have in mind. Any questions here? I think this is an important starting point, which I think you can ask. You already asked me about it, but now I'm telling you how coupling or interaction of electromagnetic field, a mu, with a Dirac particle is introduced. That's exactly the answer to that question. That's the way how it looks like. So electromagnetic field is not a matrix, it's just a four-component vector, a mu on x. And the coupling is coming through this product, gamma mu by a mu. No, and then there is a constant E which regulates the strength of this coupling. And this is what we call electric charge. Okay.
So here, also the field are classical, right? So here the spinor field and the electromagnetic field are
so far we are considering situation. You might think about this situation as being classical. In which sense? In a sense that we don't do the second quantization. For the moment, we are considering a theory of one particle. Of course, we are treating now the system. It's not classical. I don't know what you mean by classical here. In a sense, we are considering quantum mechanics of electron, of a single electron, because we are treating psi as a wave function, like in quantum, like what you do in quantum mechanics, right? So in quantum mechanics, there is a wave function, and psi is a wave function of our Dirac particle. The point is that, as we know, quantum mechanical approach is taken by itself is inconsistent in realm of quantum field theory, because there are processes of creation and annihilation of particles, so number of particles is not preserved, so we cannot restrict ourselves just to a single particle theory, and that's why we need a second quantization, right? And we realize psi not as a wave function, but rather as an operator, and this is where second quantization comes in. But for the moment, we are just looking at psi as a wave function. And the situation we are describing looks like a first quantized theory where we treat psi as a wave function of our Dirac particle. And then we introduce an electromagnetic field. The point why I'm saying that this electromagnetic field is external, because I'm not adding the dynamical equations for electromagnetic field itself. Because the dynamical equations for electromagnetic field would be Maxwell equations. And if electromagnetic field interacts with our spinor particle, then this particle would itself serves as a source for electromagnetic field. So there will be non-trivial back reaction of spinor field on electromagnetic field. But this back reaction, for the moment, I'm completely neglecting. So I'm saying that a mu is just a given field. It's given from above. Or you can think think about this as being like God given. You are not interested to ask the question from where does it come from. It is given, and it's strong enough not to be influenced by the motion of Dirac particle itself. Okay.
Well, it's like some background electromagnetic
Yes, it's a
field.
background, exactly. This is a background field which is strong enough not to be influenced by this test Dirac particle which we put in it. But on the other hand, the presence of this electromagnetic field, of course, influences the dynamics of the Dirac particle itself. And that's the reason why we say that our particle couples to this field. So equations for this particle with field and without field are different. So definitely this mu influences the properties and the behavior of this spinor psi. Now, this new equation, which we have now, I mean, this equation with a mu, it turns out that it has a new fundamental discrete symmetry, which is a symmetry of the theory with respect to the change of the sign of the electric charge. And this is the symmetry which is also considered as a symmetry replacing a particle by its antiparticle. And to understand this, well, we first need to introduce a name for it. We call this symmetry charge conjugation. And I will denote it, the action of this symmetry, the generator of this symmetry, I will denote as this letter, which you should read as C. Squarely C. I will call it, this is because of the word charge conjugation. So charge conjugation. Let's say it's a new. It is a new fundamental symmetry. It is a new fundamental symmetry. Fundamental symmetry of the Dirac equation. Of the Dirac equation. Now, existence of this symmetry implies that there is a one-to-one correspondence between solutions psi, which I denote as psi, of the Dirac equation with a negative energy and with a negative energy, so solution with negative energy, so E is less than 0. And the wave function, which has the form psi c equals to charge conjugation acting on psi, which describes a particle with the same mass as the electron, but with positive energy, and negative electric charge, or opposite, better to say opposite electric charge, opposite sign of electric charge. Opposite sign of electric charge.
Why E should be greater than 0? Because for the antiparticle we have minus root p square c square, right? That's C bar 4.
Yeah, so as we already know, studying our Dirac equation, that this equation has solutions with negative energy, right? That's something which we have established. So negative energy means, say, at rest, it is minus mc squared. And this fact, which you see here, has a physical, I mean, the symmetry, which I'm telling, has a physical consequence, physical interpretation, which consists in saying that those solutions which carry negative energy, we should, on the other hand, look at them as being mirrors, in a way, of solutions with positive energy, but with opposite sign of electric charge. So any such solution of negative energy, we have to reinterpret through this one-to-one correspondence as solutions with positive energy, but with opposite sign of electric charge. And therefore, if we have a particle as electron, and is described by a solution psi with positive energy, as it should be, then there will be another solution which is constructed from psi with negative energy as psi c, and then symmetry applied to psi, and this solution will carry opposite charge, and it has to be treated then as what we call positron. So electrons with E less than 0 should be treated as positrons with normal situation where energy is positive. That's a fundamental thing in this theory. The existence of this theory actually, in a way, returns to our Dirac equation the status of being physical, because normally equations which lead to, or dynamical systems which have solutions with negative energy, as we know, they should be neglected. Energy must always be restricted either from above or from below. And in the Dirac equation, if you look at by itself, this is not the case. There are solutions with negative energy and with positive energy. And they are not restricted, they are not bounded neither from above nor from below. So from this point of view, you might say that you have not take this equation as physical. But on the other hand, we realize that, in fact, due to this new fundamental symmetry, you may give to the Dirac equation, to the solutions of the Dirac equation with negative energy, a new interpretation. Namely, you can treat them as solutions with positive energy, but opposite sign of electric charge. And in fact, the real understanding of what's happening with this fundamental symmetry comes only upon quantizing, upon performing the quantization of the Dirac theory. And this is something which I have not done so far. For me, psi on X here is a classical field. You may treat it as a wave function, as I said, of the first quantized theory. But on the other hand, this is psi is like a usual classical field, and that is its equation of motion. And then this symmetry, which I'm describing here, looks like a classical symmetry, which simply means that solutions with negative energy have mirrors in the space of solutions of positive energy. Any solution with negative energy has a mirror with a function psi complex conjugate given by application of this operation C to psi. Okay?
Okay, sir. So, so if we try to quantize it, the Dirac theory, so we'll use your second quantization, right?
Yeah, we will be using second quantization. In this case, there will be no any more solutions with negative energy at all, but there will be electrons and positrons. Solutions with opposite, solutions with opposite sign of electric charge, but only with positive energy. So in other words, these solutions with negative energy will go away in the second quantized theory in favor of solutions with positive energy, but with opposite charge. So this, how to say, negativity of the energy will be replaced by opposite sign of electric charge, if you wish. That is the basic idea behind it. But now what we have to do, we have to actually find how this symmetry acts on psi. So what is this operation, how it looks like, how it acts on psi.
Professor, so this is only valid if we have an interaction and an electromagnetic field background, right?
No, actually, you will see that situation is a bit different. I will describe it in a moment. You will see. You will see. I will clarify this in a second. So, what is an equation for this psi complex conjugate? So equation for the psi complex conjugate should be understood in the following way. Complex conjugate, charge conjugate, sorry, not complex conjugate, charge conjugate. Equation is given by gamma mu I h bar d mu minus E over C A mu charge conjugate potential. I will tell you in a moment what is this. Minus MC psi C equals to 0. Where this psi C is exactly the wave function which is obtained from psi by application of this charge conjugation operation. And A mu C is a charge conjugation of the electromagnetic field, which simply amounts to change the sign of the electromagnetic potential. So charge conjugation is an operation which acts on fields, and it acts on, since now we are describing the interacting theory, we have two kinds of fields. We have psi and we have A mu. This is our fields. And the charge conjugation is operation which acts on all fields which you have in your theory. It does not touch the constants. It does not act on C, on mass, on charge. It acts on fields. And so we charge conjugate psi and we charge conjugate the potential A mu. And the potential A mu, charge conjugation acts in a very simple way. So in a sense, you see that changing the sign of electromagnetic potential is exactly equivalent to changing the sign of the electric charge, because they come together. E comes always multiplied by A mu, and this is where we say E regulates the strength of the coupling of our Dirac particle with external electromagnetic potential A mu. So this is how our equation should look like for the charge conjugate particle. And of course, you see that if you compare it to original equation I started with, then it has exactly the same form, except that it acts on psi, not on charge conjugate. So again, in a sense, what we see here is an application of, or implementation, better to say, of relativity principle. Equation for original configuration psi a mu upon P-Fermi symmetry leads to an equation which, in terms of new or transformed fields, looks exactly the same as the original equation. Yeah, it looks the same, but in terms of transformed quantities, a mu c and psi c. And this is exactly what we have already implemented for other discrete symmetries, like, for instance, parity or time reversal. That's we just follow the same idea. Once we transformed our fields by symmetry transformation, our equation should be covariant. In other words, in terms of new transformed quantities, it should look the same as in terms of the original quantities we started with. Okay. Now you see the following, that the implementation of charge conjugation on the electromagnetic field amounts to the change of sign minus into plus. So if I allow myself to replace here a mu to a mu c, that would lead to appearance of plus. And that's why this means that I'm changing the relative sign between derivative d mu and electromagnetic field. But this change of sign can be easily undone by the operation of conjugation, because the electromagnetic field is real, while here, if I make a usual conjugation, due to the presence of this imaginary unit, there will be change of sign. In other words, what I will do, I will start from this equation here. This is my starting point, and I will just complex conjugate it. So in this way, what I will get can be then written as follows. Gamma mu star, right? I h bar d mu produced for me a minus sign, so I get minus e over c a mu. A mu is real, so I don't do anything on it. Minus mc acting on psi star is equal to 0. That's a usual conjugation. This is how it acts. And then you see that overall minus I can take out and write equation in the form d mu star I h bar d mu plus e over c a mu plus mc acting on psi star equals to 0. So this is the equation which we have upon applying the complex conjugation. And then to reach our goal, I will now assume that this operation of charge conjugation can be explicitly realized by applying a certain matrix to psi c. So psi c is a spinor which is charge conjugate of the original spinor psi, and I assume that psi charge conjugate is obtained from psi star by applying a certain matrix to it, by acting on it with a certain matrix, which I write in a slightly particular form, which is suitable for my further purposes. So without loss of generality, I can write it as some matrix C, explicit 4x4 matrix, some explicit 4x4 matrix, and then I multiply it with gamma 0. Gamma 0 is one of the Dirac matrices. Then I take -1 here and multiply it with psi c. This is just a statement again that psi star is related to psi charge conjugate by an action with a certain matrix And it's convenient for me to parameterize this matrix in this particular way. You will see it in a moment why. Okay. So in other words, if you want to see what is psi charge conjugate from here, you see that this is C gamma 0 acting on psi star. If you just invert this formula, put this matrix C gamma 0 to the left, then this is how your ansatz for psi charge conjugate looks like. Equation we are looking at is C. We take psi charge conjugate as C gamma 0 psi star, or other way around, psi star is C gamma 0 minus 1 psi charge conjugate. Then we substitute this in our Dirac equation, and then we get gamma mu star C gamma 0 minus 1, then I h bar d mu plus, no, let's write it as minus E over C, but now I'm putting this here already, charge conjugate electric field, electromagnetic field. And then here I have to write plus MC. And in principle, I have to write C gamma 0 minus 1, but I will compensate this by multiplying from the right by C gamma 0. And then I have to close this and write here what I have to write here is psi already charge conjugate, and this must be equal to 0. So this is an equation we get. And then you see that if I want to restore the original, the form of the Dirac equation, which is looking the same in terms of transformed fields. So in other words, we have minus MC acting on psi. If I want to restore this form, then I have to require that this transformed gamma mu star should simply give me minus gamma mu in order to change the sign plus here in front of MC term to minus. So I have to say then that C must be such that gamma mu star multiplied with C gamma 0 minus 1 must be equal to minus gamma mu. Or from here you can also see that if you multiply it with C gamma 0 minus 1 from the left and C gamma 0 from the right, then this is the same as to have C gamma 0 minus 1 applied to gamma mu, C gamma 0 equals to minus gamma mu star. So from this equation follows. The first question which arises here is if such a matrix C, which has this property, exists, because this transformation formulas should be valid for all mu. Mu is 0, 1, 2, and 3. For all gamma matrices, it should be valid. Essentially, what is done here is a transformation, which, if you look at this formula, it takes matrix gamma mu and it sends it to minus gamma mu star. But this transformation, gamma mu to minus gamma mu star, is, as you can easily see, is automorphism of Clifford algebra. of the Clifford algebra. Which means that under this transformation, the Clifford algebra is not changing. It turns to itself, right? Because it's quadratic in gamma matrices, so minus sign will be cancelled when you replace each gamma matrix by minus gamma mu. But then star, since coefficients in Clifford algebra are all real, then application of star will transform the algebra to itself. So in other words, what you see here is an automorphism of the Clifford algebra. But on the other hand, we know from the Pauli theorem that any automorphism of the Clifford algebra in 4 dimensions is internal. In other words, there should exist a unitary matrix such that, let's write it as a unitary matrix U, such that if you take U and you apply it to gamma mu, say star, U minus 1 with sign mu, you will get gamma mu. So transformation from a set gamma mu minus gamma mu star to gamma mu is done by unitary transformation, is done by simply unitary transformation. In other words, such a matrix C, which then related to U by the formula C gamma 0, must exist. Must exist, and we will find it in a moment. And we will find it explicitly in a moment. Its form depends its explicit form depends on the representation of gamma matrices we use. It will have one form in the Dirac representation, and it will have other forms in other representations. Okay, so this is what we have. And now we come to another important point. Namely, we can look at the following question. So we know that our spinor, 4-component spinor, transforms under Lorentz transformations. In particular, it transforms under the group of proper orthochronous Lorentz transformations. So in other words, under SO plus 1, 3. And an interesting point, an interesting observation is that, in fact, the charge conjugate spinor transforms under the same transformation under which psi transforms. So if we say that psi undergoes under Lorentz transformations the multiplication by matrix S, where S, as we know, is given by exponent of 1 over 4 gamma mu omega mu nu, right? So this is a Lorentz transformation for a spinor psi. Then for psi conjugate, charge conjugate, we will find the same formula, S multiplied by charge conjugate. And this is a consequence of these relations here, which I now demonstrate that this is indeed the case. So you see, if I consider a charge conjugate spinor, and then I multiply it with C gamma 0 to produce charge conjugate spinor, according to this formula here. Then under Lorentz transformation, this quantity, where does it go? It goes to C gamma 0 S star charge conjugate Lorentz transformation multiply with psi star. So I've just taken this transformation here and applied charge conjugation to it. Then I can write it as a C gamma 0 S star C gamma 0 minus 1 C gamma 0 psi star. And so this is my psi charge conjugate, and this is a transformation of transformation of S star. And we can look at it in more detail. What is this? So C gamma 0 S star, C gamma 0 minus 1 is, now I substitute explicitly what is this. So I have exponent 1 over 4 gamma mu star, omega mu is real, so these parameters are real. C gamma 0 minus 1, and then using the property of exponential, I can actually raise this C gamma 0 into the exponent. So this is exponent of 1 over 4 C gamma 0 gamma mu star, and then I write C gamma 0 minus 1 C gamma 0 gamma nu star, C gamma 0 minus 1 multiply with omega mu. So I raised C gamma 0 on the left and on the right inside exponent by using the property of exponential. I hope you understand here what I'm doing. And then you see that according to the charge action of this charge conjugation on gamma mu star, you see using this formula here, the result will be minus gamma mu for this block and minus gamma nu for this block. And so minuses cancel and you get the same Lorentz transformation S. So in other words, if I continue this formula of transformation of psi charge conjugate, I see that what I'm getting is simply S back multiply with psi charge conjugate. Moreover, as I said, if you introduce U as C gamma 0, then it's natural to require that this transformation U is unitary, because the equivalence of gamma matrices gamma mu and minus gamma mu star will be then unitary equivalence of two representations of the Clifford algebra. And this requirement, as you see, amounts to the following. So if I take U dagger and requires that this is 1, then I get C gamma 0, gamma 0 dagger, C dagger. But gamma 0 is Hermitian matrix. And therefore here I will get simply C dagger, and this must be equal to 1. So matrix C itself must be unitary. And then if I look at my equation here for transformation of this Lorentz representation S, then you see the following, that what is written here can be, in terms of a unitary matrix U, can be written as U, S star, U minus 1, or U dagger, because U minus 1 is U dagger, is equal to S. So this is the property of the Lorentz transformation from SO plus 1,3, which we derive in this way, which shows, in fact, that S star, complex conjugate representation, complex conjugate Lorentz representation S star is related to S by means of this formula, U dagger S U. You see, S star is U dagger S U. And mathematically, this fact means that the original representation of SO plus 1,3 on 4-dimensional spinors and its complex conjugate representation, this is this S star, they are simply a unitary equivalent. This means unitary equivalent of two different representations of S and its complex conjugate.
What what if we also add the time reversal operator here in unitary?
Not for the moment. So time reversal we are not touching for the moment. I'm just talking about this continuous subgroup of SO plus 1,3, and we know that representation, Lorentz representation of this subgroup SO plus 1,3 on 4 component spinors is reducible. You remember this? It's reducible. And on the other hand, we now find a new property of this representation, namely, if we complex conjugate it, that in reality, we don't get really a new representation, but we get a unitary equivalent representation. And representations for which complex conjugate are equivalent to the original representations, these representations are called pseudo-real. 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 And therefore, from here we learn that representation of SO plus 1,3 on 4 component Dirac spinors, So spinor representation, in other words, spinor representation on 4 component spinors is reducible. This is something which we learned before, is reducible. And it is pseudo-real. Reducible and pseudo-real, we just learned about it. And pseudo-real. That concerns the reality property. It would be completely real. It would be real if this unitary matrix U would be 1. Then such representation you would call in representation theory real representations. Representations for which complex conjugate are unitary equivalent to the original representation, they are called pseudo-real. No, and finally, if in general S star is not related to U to S by unitary transformation, then such representations they are called complex. Complex means really that when you make a complex conjugation, that's another. I mean, when you take complex conjugation, you always get a representation. So what is a representation? If you take 2 group elements, A and B, then this is a homomorphism which satisfy the relation rho AB is equal to rho on A multiplied with rho on B, where A and B are any 2 elements of your group. If you complex conjugate this representation, that still will be a representation, right, of the same group. And then the question which you can ask is, if this rho star, how it's related to rho? Is it new? Is it completely new? Is it unitary equivalent to the original representation, or is it absolutely the same as the original representation? And according to this, I mean, the answer to this question gives a classification of representations as real, pseudo-real, and complex. And for the case of the Lorentz representation of SO plus 1,3 and 4 component Dirac spinors, we learn that such a representation is pseudo-real. Now, that's interesting. That's something you will learn here. Now, you can ask the following question. So maybe this is something which you just asked me. So what happens if electromagnetic field is absent, if there is no electromagnetic field at all? So in this case, if there is no electromagnetic field, if you just now switch off this field and look back on what you know about the charge conjugation, then you see that this transformation, psi goes to psi charge conjugate, is just a novel discrete symmetry of the Dirac equations. That's another discrete symmetry, simply discrete symmetry of the original Dirac equation. So what it does, why it's a symmetry, you can ask why it's a symmetry. It's because it transforms solutions into solutions of the Dirac equation. So if you have one solution which you call psi, then if you apply this operation of charge conjugation, you will get another solution of the same Dirac equation. Moreover, this symmetry, this discrete symmetry, so in this respect, it's very similar to, say, for instance, parity or time reversal. So it acts in the same, in a similar way. It transforms solutions into solutions. And so in this respect, you can say that, you can actually now answer the question, which solutions to which solutions? And it turns out that this symmetry maps positive energy solutions into negative energy solutions and vice versa. And this you can see from the following argument. So if you take this symmetry of charge conjugation, act on positive energy solution, which is obtained by acting on the Dirac spinor U by our projector on positive energy solutions, which I have introduced in the last lecture, then this can be written in the following way. So this C gamma 0, and then you get lambda plus complex conjugate U complex conjugate, according to how this symmetry acts, right? And then you can explicitly substitute and complex conjugate the action of this operator. And you remember, this is gamma 0, now star E energy, minus C gamma I star PI, plus MC squared, multiply with identity matrix, divided by 2MC squared. So this is my lambda plus star. And then I have U star, but U star I will write now in the following way. I write C gamma 0 minus 1, C gamma 0 U star, like this. So I introduce this insertion of identity. And then you see that acting from the left and from the right with C gamma 0, I now put these two matrices closer to each of these conjugate gamma matrices, and then they will be replaced by usual matrices, but with a minus sign, according to how this operation of charge conjugation acts. So what I will find is minus gamma 0 E plus C gamma I PI plus MC squared multiplied by identity divided by 2MC squared. No, and then I will get C gamma 0 left over acting on psi star. And this is what is written down here is nothing as a lambda minus projector acting on, and this is our symmetry. This is our symmetry acting on U. So in other words, you see you have the following commutation relation. This symmetry transformation of Church conjugation what it does, it intertwines, as we say, operators, projectors on the positive and negative energy. This is how it acts. When it passes through lambda plus, it gives lambda minus, and vice versa. That's why I'm saying that positive energy solution under the charge conjugation go to the negative energy solutions and vice versa. So it's a symmetry which maps positive solutions into negative solutions. Symmetry in a sense that it transforms solutions into solutions. You have a solution, apply symmetry, you get another solution. The difference between the solutions is that one has a positive energy, another, upon applying the symmetry, will have a negative energy. Now you can do the same trick with helicity. Because for helicity, you also have projectors on solutions of positive helicity and negative helicity. And then there is this charge conjugation. And so projector C gamma 0, and then projectors are plus minus, you remember, gamma 5 star. Here I'm applying this conjugation, which is in our operation C is implied. So gamma 5 star, gamma 0 star, gamma I star, pi, divided by modulus of p. That's a conjugation of this helicity projectors. And then again, you have U star. And U star, you write again as gamma 0 minus 1, C gamma 0, U star, like this. And so again, you take this object, put C gamma 0 close to these matrices, and then use the charge conjugation, and then you will see that what they produce for you, because you have here 3 gammas, and they will change the sign under charge conjugation. They will turn, first of all, to the matrices without star, but everyone comes with a minus sign, and so altogether you will get the change of plus minus to minus plus, and then gamma 5, gamma 0, gamma I, pi, divided by modulus of p, and then this operation applied to u. In other words, you get this projectors minus plus, depending on p, acting on charge conjugation of u. And so intertwining of helicity happens then in this way. Plus minus is minus plus, and then charge conjugation. In other words, solutions with positive helicity go to solutions with negative helicity and vice versa. And so in general, we can now conclude that this operation acts like positive energy solution, and the definite helicity goes to negative energy solution, and opposite helicity and vice versa. Okay, so this is how this symmetry acts on solutions of the Dirac equation, even in the absence of electromagnetic field, because if there is an electromagnetic field, then charge conjugation also implies that electromagnetic field changes the sign. It's a charge conjugation of electromagnetic field. But if electromagnetic field is absent, there is nothing to charge conjugate from the point of view of electromagnetic field, and therefore what you then get is just a statement about the charge conjugation being a new discrete symmetry of the Dirac equation, which transforms solutions into solutions. Now, up to now, all considerations I have done of charge conjugation did not depend on any particular representations of any particular representation for gamma matrices. And from this point of view, they were of a general character. Now, further determination of this matrix C, concrete matrix C, relies on a representation chosen. And for instance, for the Dirac representation, of gamma matrices, we can choose this matrix C to be equal gamma 2 multiplied with gamma 0. And then you can see that this matrix exactly does the job which we need. So C gamma 0 in this case is simply gamma 2. And then we see that if we take gamma 2 minus 1 and multiply it with gamma mu, gamma 2, then what happens is that we will get minus gamma mu star in this representation. That's exactly what this matrix gamma 2 will do for us. Let's see. So gamma 2 squared is equal to minus 1. Therefore, this can be replaced by a statement that if I replace gamma 2 minus 1 with minus gamma 2, then this is the same as to say gamma 2 gamma mu gamma 2 is equal to gamma mu star. Right. Gamma 2 gamma 0. Yes. For instance, you can see that in the Dirac representation, the matrix gamma 0 is diagonal matrix, and it's given by 1 minus 1. So from this point of view, it is real. And then you see that what you get is gamma 2 gamma 0. Gamma 2 is equal to gamma 0 because gamma 0 is real, and this is indeed the case because gamma 2 and gamma 0, these two anti-commute, and therefore you get minus gamma 0 gamma 2 gamma 2, but gamma 2 square of gamma 2 is minus 1, and therefore you return back to gamma 0. So for gamma 0 it is working. Now for the other matrices, gamma I, this you have to go to the Dirac representation to see explicitly what happens with gamma I. So let's recall us what is this representation. So in this representation, we recall that gamma I, the other matrices, gamma I are simply given by minus, but they are given by here 0 sigma I minus sigma I, where sigma I are Pauli matrices. And here you have to distinguish, say, for instance, matrices matrices sigma 1 and sigma 3 are real, and therefore under complex conjugate, gamma I, gamma 1 and gamma 3 will be unchanged, and for 3 the same, so 1 and 3 they are unchanged, while for gamma 2 you will get that you have sigma 2 in this case, and when you complex conjugate sigma 2 is a matrix which contains I and minus I, it will change sign. So gamma 2 will be changing the sign. So it's minus gamma 2 under complex conjugation. And then you see exactly that gamma 1, gamma 3 will behave themselves exactly like gamma 0 that on the right hand side you will get gamma 1, gamma 3, and on the left hand side gamma 1, gamma 3 will anti-commute with gamma 2, so you will get minus sign, but then gamma 2 squared is minus 1, and then you will get what you want. For gamma 2, this is different, so you will get gamma 2, gamma 2, gamma 2, and on the other hand, conjugation of gamma 2 does minus gamma 2, and you see that since this is minus 1, you get exactly what you want. Minus gamma 2 is equal to minus gamma 2. Indeed, for Dirac representation, C equals to gamma 2, gamma 0 is a matrix which satisfies the required property. What it does when it acts on gamma matrices in the Dirac representation, that's therefore we found an explicit realization of this C for this case. And then we also see that unitarity conditions are satisfied in addition with the following properties. So C squared is equal to 1, that you can easily see from gamma 2, gamma 0, gamma 2, gamma 0, gamma 0, gamma 2 gives minus gamma 2, gamma 2, gamma 0, gamma 0. Gamma 2 is minus 1. Gamma 0 is 1. And so you get 1. So C squared is 1. That's one property of this matrix. The second property is C star is equal to minus C for this matrix. That's again easily checked. So gamma 2, gamma 0 conjugate gives me gamma 2 conjugate, gamma 0, and gamma 2 conjugate is minus gamma 2, gamma 0, so this is minus C. And from these properties, you check that C dagger is equal to 1. You also need to use transposition properties of gamma 2 and gamma 0 in this representation. So this is the same as C complex conjugate and transposed. You will get minus C transposed. This is minus gamma 2, gamma 0, gamma 0 transposed, gamma 2 transposed. Gamma 0 transposed is the same as gamma 0, because gamma 0 in the Dirac representations matrix 0, 1, 0, 0, minus 1. So it does not change under transposition. And therefore, this is 1 here. And then you get minus gamma 2 transpose. The gamma 2 transpose is minus gamma 2. Is minus gamma 2 or it is gamma 2? It is minus gamma 2. Let me see if I have not done any mistake here. Okay, check me. In any case, it should come out from here that C dagger must be equal to 1. Must be equal to 1. I think I'm making somewhere a little mistake.
It should minus, right? Because it consists of I.
Sorry, what do you say? Yes, it should gives me plus, right? Because when I so I'm not making mistake. It's just plus here. So then I'm finishing minus gamma 2, and then this is minus 1, and so I'm getting 1. And why it is so? That is because gamma 2 transpose gives me 0, 0, sigma 2 transpose with a minus, and then sigma 2 transpose. But sigma 2 transpose is minus sigma 2, right? Because what is sigma 2? Sigma 2 is 0 minus I, or I minus I 0, right? So when I transpose it, I will get extra minus sign. And therefore, here I will get 0 sigma 2 minus sigma 2 0. Therefore, this is gamma 2. Yeah. So under transposition, gamma 2 is unchanged, and therefore CC dagger is 1. So these are the properties of matrix C, which you explicitly derive in this representation. No, and then charge conjugate spinor in the Dirac representation. Explicitly, you realize it as C gamma 0 psi star. And this is gamma 2 psi star. And if you wish, you can also write it in the following way. This C gamma 0, you may write as C, and then you introduce psi bar, which is explicitly psi star transposed, so it's a row vector, multiplied with gamma 0. And so if you take then psi bar and transpose it, so to get a row, you will get here gamma 0 psi star. And therefore this formula can be also written as C psi bar transposed. So psi bar itself is a row, but psi bar transpose is a column. So this is column. Under transposition, row goes into column, and therefore here this is matrix C acting on the column, which is now represented with the help of the Dirac conjugate spinor. And in many books, you will see that this operation of charge conjugation is indeed written with the help of the Dirac conjugate spinor in this way. So this is very often you see this representation. Now,
Professor, this expression is right, right? Integration xi bar equal to 1.
Yeah, it's absolutely correct. Yeah, it's absolutely correct. It's just that I paused a little bit to deduce that under transposition, the matrix gamma 2 is unchanged. And then this leads exactly to 1 on the right-hand side. So everything here is absolutely correct. So CC dagger is equal to 1. This is unitary C as we required as is implied by unitarity of U of the matrix, which relates to representations of the Clifford algebra. Yeah, so this is where we got this statement about the unitarity of C, and indeed we see that with our choice of C being gamma 2, gamma 0, this is fulfilled. CC dagger equals to 1 is fulfilled. Now, one thing, it's a remark which I also give here is the following. Look, if we so with respect to matrix C in this representation, we also have the following property. So if you take C minus 1 gamma mu C, then this is minus gamma 0 gamma mu star gamma 0. So here I'm using this relation that C gamma 0 minus 1 gamma mu, C gamma 0 is equal to minus gamma mu star. What I've simply done, I just explicitly open minus 1. I've taken minus 1, so then I get gamma 0 minus 1, but this is the same as gamma 0. C minus 1 gamma mu C. Gamma 0 is equal to minus gamma mu star. And then I put this gamma zeros to the right, and then this equation which you get. To the right, I mean I multiply it with gamma 0 from the left and gamma 0 from the right. But on the other hand, what is written down here is nothing else in the Dirac representation as minus gamma mu transposed. Gamma mu transposed. So complex conjugate matrix multiply from the left and from the right by gamma 0 is the same as minus gamma mu transposed. And so alternatively, in the Dirac representation, you can characterize this matrix C by the property that acting on gamma mu, conjugating gamma mu with this unitary matrix C, gives you a minus gamma mu transposed. Gamma mu transposed. And by the way, what is written on the right-hand side, also a representation of the Clifford algebra. And again, this shows that the unitary equivalence of gamma mu with gamma mu transposed with the other representation of the Clifford algebra is performed with the help of the unitary conjugation by the matrix C. That's a remark which that's a consequence which we immediately derive from what we now learned about this matrix C. And also here we can deduce another interesting simple consequence that if we have C minus 1 gamma mu C given us minus gamma mu transpose, then we can check what happens with gamma 5 when we conjugate it in this way. And this simply amounts, it turns out it amounts to gamma 5 transposed, right? Gamma 5 transposed. Because gamma 5 is a product of gamma 0, gamma 1, gamma 2, gamma 3. And when you apply C minus 1 C, then you see that this transposes each of these matrices, so it becomes gamma 0 transposed, gamma 1 transposed, gamma 2 transposed, gamma 3 transposed, and then you can rewrite it as the original matrix gamma 5, but just transposed. And then on the other hand, you know that in the Dirac representation, this gamma 5 is symmetric, so it does not change under transposition. But then under this result, it follows that since C minus 1 gamma 5 C is equal to gamma 5, from here it follows that C actually commutes with gamma 5, right? So what is written down here, that's if I put C to the right, that's exactly the condition that C commutes with gamma 5. And sometimes this property is also interesting and should be taken into account in some considerations. So in any case, this is a consequence of the explicit representation for C in the case of Dirac representation. Now,
but isn't gamma 5 responsible for the creation of C charge conjugation? Because we use gamma 5 for the antiparticle.
No, gamma 5 I've used to define what is called Weil spinor, because I use gamma 5 to define projections, Weil projections. Remember that chirality. This is related, gamma 5 was related to chirality. I defined chiral projections with the help of the matrix gamma 5. And now we have learned that these projections will commute with this matrix C, which is responsible for the charge conjugation, and that's a consequence of of these equations here. Now, in summary, so the Dirac theory is invariant under charge conjugation of a spinor supplied with a simultaneous change of electromagnetic field to minus electromagnetic field. And the physical meaning of this charge conjugation operation is that any physically realizable state of electron in the field A mu corresponds to a physically realizable state of a positron in the field minus A mu. And so operation of charge conjugation changes electrons with negative energy and spin up to positrons with positive energy and spin down. And this is, yes, what we have derived today. And if we have a solution of the Dirac equation, say with a negative energy, and call it psi minus, so this is wave function corresponding to a solution with negative energy, and an electric charge which denoted by E, then we should take as a physically realizable or physically relevant quantity not this psi minus, because it's a solution with negative energy and for this reason makes no sense, but rather it's charge conjugate solution, so psi charge conjugate, which has then positive energy and given explicitly by C psi bar minus transposed. Yes, so this charge conjugation applied to this psi minus. And this solution, this psi C plus, will then describe a particle with a positive energy, so physical particle, but with different sign in comparison to the sign of original electron. And this difference, that's exactly due to this charge conjugation we have. And therefore, we can identify the positive energy plane waves, psi, let's call electron R x t, given by solutions U plus R depending on momentum P, exponential minus I H bar P mu x mu, and psi positron R on xt been given by C, multiplied with, or multiplied, C multiplied U minus, U bar on P minus, with minus meaning that it is negative energy solution, but it's charge conjugate now. So let's write it this way: psi bar minus charge conjugate transposed, which means that this is charge conjugate of psi minus, or psi, psi minus, exponential minus I H bar P mu x mu, as wave functions of electron and the positron. So these are wave functions. Say wave functions of electron and positron. Electron and positron. And now, if we are return back to our solution, and so this is, if you wish, you can treat as a charge conjugate of V minus, spin V minus, you remember, R on P, V minus, because this is what is written down here, corresponds to V minus, for the reason that, as you remember, we introduce V minus on minus P as V minus on P as U minus on minus P. You remember that's way I introduced this spinors V as a positive or energy and negative solutions, but with opposite sign of momentum. And so then you can think about this as coming from charge conjugate of a plane wave, H bar P mu x mu, under the operation of charge conjugation, and then a sign here of plane wave is changed because charge conjugation involves usual conjugation, complex conjugation, and therefore plane wave here changes its sign from plus to minus under this operation. To say that I have to return back to our general solution of the Dirac equation, which we have represented in terms of plane waves, then to say that it would be natural to treat the amplitude, which is given in terms of this coefficient BR, in the solution, general solution of Dirac equation, as an annihilation operator of electron. So annihilation operator of electron, while then dr star, which appears as another amplitude standing in front of the IH bar P mu X mu, as a creation operator of a positron. Creation operator of a positron. And this is, again, that's consideration which I'm doing here, relates to the physical interpretation. I would like to associate to the positive and negative energy solutions in the general expression for the Dirac equation. So negative energy solutions I would like to reinterpret from the point of view of our new understanding of this charge conjugation symmetry as those which correspond to actually positive energy solution, but for another particle which we call positron. And correspondingly, this gives an interpretation to the amplitudes which we have in general solution of the Dirac equation. These are amplitudes which I introduce as BR and DR star, as correspondingly annihilation operator of electrons and the creation operator of positrons. That's something which we can further understand when we come to the quantization of the Dirac equation and understanding the quantum theory. Then it's, I think it will become very much clear. And so clarity becomes very transparent in that case. And the final topic, which concerns this consideration of reality properties and the charge conjugation, concerns with the issue of so-called Majorana Spinors. Majorana Spinors. We already learned that there are 4-component Dirac spinors. There are also Weyl spinors, which are 2-component complex spinors. And now I would like to introduce another kind of spinors, which are called Majorana. And so we know that a Dirac spinor in 4-dimensional Minkowski space has 4 complex components. So Dirac spinor, general Dirac spinor, has 4 complex, 8 real components. So 4 complex, or if you wish, 8 real components. 4 complex components, which is equivalent to 8 real degrees of freedom. 8 real degrees of freedom. It is possible to reduce a number of independent components of this Dirac spinor by imposing certain conditions which are compatible with Lorentz transformations from SO plus 1,3. One of these conditions is a Weyl condition, which we have discussed, and that allows to define the Weyl spinor, which has 2 complex components. two complex components. And this spinor transforms, as we know, irreducibly under SO plus 1,3. Now we can impose another condition, which is called Majorana condition. Which is a condition that says take spinor psi and identify it with its charge conjugate. That is a Majorana condition. In other words, Majorana condition is a condition that states that particle is its own antiparticle. Particle becomes its own antiparticle. Now, we have seen
with fermions only, right?
Yeah. Particle is its own antiparticle. Particle here is a Dirac spinor. And the special Dirac spinor, which satisfies this condition when psi is equal to psi complex charge conjugate, then such a spinor we called Majorana. Of course, this condition I allow myself to impose because I know that psi and psi charge conjugate transform in the same way under Lorentz transformations. So this condition does not break Lorentz symmetry. It is Lorentz invariant. The Lorentz transformations pass through because psi transforms under Lorentz transformations in the same way as charge conjugate spinor, right? This is what I showed before. And this is important. An explicit form of the Majorana spinor depends on the chosen representation for gamma matrices. Because, as I said, the explicit form of the charge conjugate matrix C depends on the representation chosen. For instance, in the Dirac and Weil representations, in both these representations, C is given by gamma 2, gamma 0, and therefore, when you impose this Majorana condition, that means that you have to solve the following equation. Psi is equal to C gamma 0, psi star, which is simply gamma 2 psi star. And so this is Majorana conditions and how it looks like. Psi is equal to gamma 2 psi star. And if you think about psi as being written in terms of two-component spinors, say phi and the chi, and you plug in this representation into this equation, so you write explicitly gamma 2 as 0 sigma 2 minus sigma 2 0, and then phi star chi star, you see that from these conditions you can express chi, say via phi star, and the answer will be that such a spinor, such a Majorana spinor in the Dirac representation of gamma matrices will have the following form. It will be simply phi here, unrestricted, two-component complex, and here there will be minus sigma 2 phi star, like this. This is how it will look like, where phi remains to be an arbitrary two-component complex spinor.
Professor,
yeah?
Can you repeat this part, which you said?
Sorry?
Can you repeat this part as minus sigma 2 phi star?
It's a solution of this sigma 2. Okay, sorry, sigma 2 probably I have to write with an upper index. Indeed. Let me write it with upper index. That is a solution of this equation. So from this equation, you see that phi is equal to sigma 2 chi star, and chi is equal to minus sigma 2 phi star. From these equations, only one is independent. You can take this equation expressing chi via phi, because the upper equation follows from this one upon conjugation. If you conjugate, then you will get here minus sigma 2 complex conjugate phi, but sigma 2 complex conjugate is minus sigma 2, and so you get sigma 2 phi, and then you multiply it with sigma 2, and sigma 2 squared is 1, and so then you return back to this equation here. So from these two equations, only one is independent, and this is this one. You can take and substitute it here, and so then this is the form of Majorana spinor. This spinor solves the Majorana condition. So this is therefore Majorana spinor. This is how it looks like.
So if particle is equal to its antiparticle.
Yeah, exactly.
So if particle is equal to its antiparticle, then why we have 4 bases here?
Sorry, why we have
4 components here? Means generally 2 is for particle, 2 is for antiparticle in the Dirac basis. But
no,
if
we
particle,
have we impose we have a restriction now, because we said that this condition is the one which must be satisfied, and we impose it and solve it. So
but this also means, right, the particle is equal to its antiparticle, so we don't have any antiparticle, or they are the same. So we should have only 2 bases. One is for plus half and minus half.
No, that's why you have two component spinor phi to be independent. You have two component spinor phi to be independent, because the other two components are now simply obtained by complex conjugate of the first two components. So it's not an arbitrary 4-component complex spinor, but it's a restricted spinor in a sense that it has only 2 independent complex components.
So inside this minus sigma 2 phi star, we have two components, right?
Absolutely, yeah. But they are obtained from this phi, which is upper, by complex conjugation. So in this respect, this phi star is not new. It's obtained from phi by complex conjugate. It does not introduce new degrees of freedom. All degrees of freedom are sitting here in phi.
Okay, so they are now dependent on phi.
Yes. It's a complex conjugate. Before it was chi, and chi was unrestricted, and it's not related to phi. So the number of degrees of freedom was 4 complex components. Now, upon I solved the Majorana condition, I obtained that chi is expressible via phi. How it's expressible? It's equal to minus sigma 2 multiplied by phi star. And so only phi remains to be independent. And in this way, it has the same number of complex components as the Weil spinor. It has 2 complex components, just like a Weil spinor. But the meaning is different. Weil spinors are obtained by means of chiral projections, and Majorana spinor is obtained by solving the Majorana condition. And this is this one we are solving here. Moreover, there exists yet another representation of gamma matrices in which the Majorana condition becomes very, very simple and transparent. And this representation of gamma matrices is called Majorana representation. So Majorana representation is a representation in which all gamma matrices, all gamma mu are imaginary. Imaginary. So that the Dirac operator contains, in fact, only real coefficients. And explicitly, I will write down straight away this representation. This representation where gamma 0 is 0, sigma 2, 0. Yeah, so sigma 2 is purely imaginary, has purely imaginary components. Gamma 1 is given by I sigma 3, 0, 0, I sigma 3. Gamma 2 is equal to 0 minus sigma 2, sigma 2. Also contains only sigma 2. And finally, gamma 3 is a matrix which is minus I sigma 1, 0, 0, minus I sigma 1. Also purely imaginary. So you can check that Clifford algebra relations for these gamma matrices will be satisfied. And of course, this means, again, by Pauli theorem, that there exists a unitary matrix that transforms, say, Dirac representation into this new Majorana representation by means of conjugation with this unitary matrix U. So if gamma mu are Dirac and this Majorana gamma matrices, then the relation is gamma mu Majorana, where you can check that explicitly this matrix U is given by 1 divided by square root of 2, 1 sigma 2 minus 1. And this matrix is explicitly unitary. U dega U is equal to 1. Now, the Church conjugation matrix should be determined from this condition, C gamma 0 minus 1, gamma mu is equal to C gamma 0 equals to minus gamma mu star. But in this Majorana representation, we know that this gamma mu star is simply minus gamma mu because all gamma matrices are purely imaginary, and therefore here I have gamma mu. And from here you see it follows that C gamma 0 then must simply commute with all gamma mu's, so the result must be equal to 0. And this means that C gamma 0, the only way you can commute non-trivial matrix, the only matrix which commutes with all gamma mu's in 4 dimensions, this is identity matrix. And from here you conclude that C is simply gamma 0. And when C is gamma 0, then Church conjugate spinor, Church conjugate, is given by, in this representation, by C gamma 0 psi star. That means gamma 0 psi star. And therefore, here you get psi star. So in this representation of gamma matrices, Church conjugate spinor is simply complex conjugate spinor. Church conjugate is complex conjugate. And therefore, in this representation, in the Majorana representation, Majorana condition becomes extremely simple and transparent. So Majorana condition, or condition defined in Majorana spinor in Majorana representation for gamma matrices, in Majorana representation, becomes a condition that psi, original spinor, coincides with its Church conjugate, but its Church conjugate is simply complex conjugate spinor, which means that in the Majorana representation, spinor psi is simply real. Real, that means it has simply 4 real components. 4 real components. And in this representation, you can also see that S, matrix S of Lorentz transformations must preserve reality of a spinor. So spinor psi is equal to psi star, and that means that psi is real, and therefore S acting on it must transform a real matrix into real matrix. So this means that in this case, S itself is real, and that's you of course can easily see from the fact that it's given by 1/4 gamma mu omega mu nu. In the Majorana representation, each of the gamma matrices is real, and then the product of these two real is imaginary. Sorry, and the product of these two imaginary gamma matrices then gives you a real result. And so in this representation, then Lorentz transformations are realized by real matrices. So S is a real matrix in this representation. Is a real matrix in this representation. Okay, that's basically what I wanted to tell you in this last lecture. And in the new semester, we started, I think, with quantum theory of the Dirac equation. So essentially, we quantize it and construct a propagator for the Dirac field. And then we'll try to develop our theory further. Okay, so I think I finished. So if you have questions, please ask.
Professor, so if for example, if you want to find the speed of the particle using the Dirac equation, how can we do this?
What do you mean by this? So since now we have a speed, now we have a description of our particle. We are describing our particle by means of a wave packet. If you wave packet, it means we have a wave function, and the particle would be a wave packet in quantum mechanics. And wave packet has a certain notion of velocity. There is a group velocity, there is a phase velocity. If you want to think about spinor as just a relativistic particle, then its velocity is found as usual by using the relativistic formula, which relates a momentum of a particle to its velocity by means of this formula, mv divided by square root of 1 minus v squared over c squared. So velocity is something which you give your particle as an initial condition. If this particle is free, then it will go uniformly, keeping its velocity and rectilinear, so uniform rectilinear motion. So I'm not quite understanding what you mean by velocity here. In which sense you want to know velocity of your particle? Particle is a relativistic particle. It's a massive relativistic particle. Its velocity is related to momentum by means of this relativistic formula.
No,
and there is a formula for the energy. Yeah.
If we want to write the wave equation for the particle.
No, wave equation. We know we are writing it for.
That means from wave equation we get the velocity from there only. But for this case, how is it possible?
No, again, if you are talking about waves, then there is a notion of group velocity and there is notion of a phase velocity, and it depends which one you would like to write down and understand.
Because I mean, I wanted to prove this that for Majorana case, the particle travels at c, right? I'm not wrong.
No. It depends. If it's an electron is not moving with the speed of light. You know, it's massive particle. It cannot move with the speed of light.
but they are also not Majorana. So, so if there is Majorana particle, they'll travel at the speed of light.
Majorana particle, we don't know if Majorana particles exist in nature. What we know is that pseudoparticles can be can be of Majorana type. And pseudoparticles, these are typically collective excitations, which you find, for instance, in condensed matter theory. Moreover, such conditions and Majorana conditions are also something which often arise in string theory. But I think in reality, we don't know if fundamental or elementary particle of Majorana type does exist in nature. Pseudoparticles, yes. Pseudoparticles can be of Majorana type, and they are known in condensed matter physics, indeed.
Yeah, okay, sir.
Professor, I have another question.
Yeah.
Related with, we saw that the charge conjugation operator changed the helicity of the particle. And then I wonder if this is somehow related with the fact that of the interpretation of Dirac of the antiparticles are particles going backward in time, because if we interpret the helicity as the projection of the spin in the direction of the momentum. If you can say some words about this.
Yeah, so there are several ways. There are several ways how to think about antiparticles. And so there is a picture which Dirac originally proposed. It's called Dirac C, which basically says that antiparticles are holes in the Dirac C. So when electron is excited and gets out of the C, then there is a hole left in the originally completely filled C, and this hole should be interpreted as positron, because when electron with positive energy goes out of the C, so there is a field C, and the C of particles with negative energy is completely filled. And then when electron gets out and has a positive energy, then the hole is left over. And this state with a kind of represented, this hole can be interpreted as positron, so antiparticle of electron. And this is the original interpretation of the Dirac C that has been proposed by Dirac. But in fact, I think in the quantum theory, we don't need such an understanding. In the quantum theory, everything becomes quite simple in a sense that there will be only positive energy solutions. The Hamiltonian, quantum Hamiltonian, not the classical one, but the quantum one, will become restricted from below. It will have a bound. And the operation of charge conjugation, operator of charge conjugation will have positive and negative eigenvalues, which means that solutions with positive charge and solutions with negative charge corresponding to positive and negative eigenvalues of this charge operator or operator which defines electric charge. Okay, so this then this interpretation becomes simply, how to say, redundant, I would say.
Okay, thank you.
I don't like very much this picture of the Dirac C. You can use it, and people often use it in condensed matter theory, but in fact, I think you don't need it when you really come to quantum theory. Once again, from the point of view of classical theory, I think the Dirac equation cannot be really accepted as a dynamical equation because it has solutions with negative energy. The wonderful thing about it is that the quantization alters this bad feature into a very good feature. basically, upon quantization, Hamiltonian becomes well-defined and restricted from below, while the operator which counts an electric charge, the charge operator, start to have positive and negative eigenvalues, meaning that you have particles with positive electric charge and particles with negative electric charge, but both particles with a positive energy. And this is something which we will consider. This is something which we derive, actually. And in fact, this is something which we should require from our quantization principle, that this is, we have to construct our quantum theory in such a way that it will have only positive energy solutions. Okay, that's would be important for the consistency, or how to say, physical interpretation, that our quantization is all right.